Have you ever looked at a curved graph and wondered, how could anyone possibly calculate the exact area beneath this curve? It seems impossible. If I asked you to find the area of a rectangle, you could probably answer within seconds. A triangle? Easy. A circle? No problem. But what about this? A completely irregular curve. There isn't a simple formula. No obvious shape. No straightforward solution. For centuries, mathematicians faced this exact problem. They knew how to measure regular shapes. But when nature presented curves, whether in the path of a falling object, the growth of a population, or the flow of a river, they were left with a question that seemed impossible to answer. How do you measure something that doesn't have a measurable shape? And then, someone came up with an idea so clever that it changed mathematics forever. An idea that powers modern engineering, physics, economics, computer graphics, artificial intelligence, and even space exploration. An idea based on something unbelievably simple. Tiny rectangles, not hundreds, not thousands, but an infinite number of them. At first, that sounds ridiculous. How could adding infinitely many rectangles ever produce one exact answer? It feels like infinity should make the problem impossible. But instead, infinity becomes the solution, and by the end of this video, you'll understand why one of the greatest discoveries in mathematics isn't actually difficult. It's beautiful. Welcome to MathnexusbyNaustenka, the place where mathematics isn't just about formulas. It's about discovering the incredible ideas hidden behind them. If you've ever wanted to understand why mathematics works instead of simply memorizing it, you're in the right place. So let's begin. Imagine you're standing beside a beautiful lake. The shoreline isn't straight, it's full of gentle curves. Now someone asks you a simple question. What is the exact area of the water? Where would you even begin? You can't use the formula for a rectangle. It isn't a triangle. It's not a circle. Its shape is completely unique. Now replace that lake with a mathematical curve. The challenge is exactly the same. We want to know the area beneath it. But there isn't a formula waiting in the textbook. For hundreds of years, this question puzzled some of the greatest mathematical minds. Because unlike regular shapes, a curve refuses to fit neatly into any familiar formula. It seems impossible, but sometimes, the smartest solution isn't to solve the impossible problem directly. Sometimes, we solve an easier problem instead. Imagine placing one large rectangle underneath the curve. Is it perfect? Of course not. Some parts of the curve stick out. Some empty spaces remain uncovered. The estimate isn't very accurate, but it gives us something. And sometimes, the first step toward perfection is allowing yourself to be imperfect. So instead of one rectangle, let's use two. Immediately, the estimate improves. Now 4 rectangles. Even better. Then 8, 16, 32. Notice what's happening. Each time we increase the number of rectangles, the empty gaps become smaller. The shape of the rectangles begins to follow the curve more closely. Without realizing it, we're getting closer and closer to the real area. Not because our rectangles are becoming taller, but because they're becoming thinner. Every new rectangle captures just a little more detail, like increasing the resolution of a blurry photograph. At first, the image looks rough, but as more pixels appear, everything becomes sharper, clearer, more accurate, and that's exactly what's happening here. Every extra rectangle makes our estimate a little better than before. Now here's the question that changes everything. What if we never stopped adding rectangles? Not 100, not 1,000, not 1,000,000, but forever. Would our estimate eventually become perfect, or would there always be tiny errors left behind? That single question gave birth to one of the most powerful ideas in all of mathematics. And the answer is far more surprising than most people expect. Let's continue our journey. In the previous part, we discovered that the more rectangles we place beneath the curve, the closer we get to the actual area. But now we're about to ask a question that completely changed the history of mathematics. What happens if we never stop making those rectangles thinner? Not 100 rectangles, not 1,000, not even 1,000,000, but an infinite number of them. At first, this idea sounds impossible. How can anyone add an infinite number of things? Wouldn't the answer be infinitely large? Surprisingly, the answer is no. And that's exactly what makes integration one of the most beautiful ideas ever discovered. Imagine you're trying to build a perfect curve using small Lego bricks. If the bricks are large, the curve looks rough and blocky. Now replace those large bricks with smaller ones. The curve immediately becomes smoother. Use even smaller bricks, and it becomes smoother still. Keep repeating this process, again, and again, and again. Eventually, the bricks become so tiny that the gaps almost disappear. From a distance, the blocks no longer look like separate pieces. They look like one perfectly smooth curve. That's exactly what's happening with our rectangles. Every time we make them thinner, they fit the curve a little better. The empty spaces become smaller. The extra pieces sticking outside the curve become smaller. With every improvement, our estimate becomes more accurate than before. Now imagine pushing this idea to its absolute limit. The rectangles become unimaginably thin. So thin that their width is almost zero. Not exactly zero, because a rectangle with zero width wouldn't exist, but incredibly close. And here's the magical part. As those rectangles become thinner and thinner, the total error also becomes smaller and smaller. Eventually, the error becomes so tiny that, in mathematics, we treat it as disappearing completely. This idea is called a limit. A limit doesn't mean we actually build infinitely many rectangles. Instead, it asks a much smarter question. If we keep improving our estimate forever, what value does it approach? And the answer is astonishing. It approaches the exact area beneath the curve. Not an approximation. Not close enough. The exact answer. This single idea gave birth to a completely new branch of mathematics. A branch we now call calculus. Now, mathematicians needed a simple way to write this entire process. Writing, add infinitely many tiny rectangles together. Every single time wasn't practical. So they invented one elegant symbol. The integral sign. Integral. At first glance, it looks mysterious. But it actually has a fascinating history. It's a stretched version of the letter F, and that S stands for sum. Because integration is nothing more than adding together countless tiny pieces. Every time you see this symbol, think of it as a machine that whispers, keep adding, until the whole picture appears. Now let's look at a complete integral. Integral of f of x, dx. Many students see this expression and immediately think it's complicated. But once you understand what each part means, it's surprisingly simple. The function, f of x, tells us the height of each tiny rectangle. Remember, every rectangle has a height. That height changes depending on the curve. Now look at the small dx. This tiny symbol confuses millions of students. But it's actually describing something very familiar. The width of each rectangle. The letter D represents an incredibly tiny change. So dx simply means an incredibly tiny width along the x-axis. Now think about every rectangle we've been drawing. Each one has a height, and each one has a width. Multiply those together, and you get the area of one tiny rectangle. Now imagine calculating the area of every tiny rectangle beneath the curve. Then adding every single one together. That's exactly what the integral is doing. Silently, perfectly, piece by piece, until every tiny rectangle combines into one exact area. And suddenly, a problem that once looked impossible becomes beautifully simple. Integration teaches us something far beyond mathematics. Sometimes, the biggest problems aren't solved all at once. They're solved by breaking them into tiny pieces, solving each piece, and putting them back together. That simple idea doesn't just explain integration. It explains how we solve some of the world's most difficult problems. But this raises one final question. If integration is really just adding tiny pieces together, how is it used to calculate the distance of how traveled, the amount of water flowing through a river, or even how build the technology we use every single day? Let's discover that in the final part. So far, we've discovered something incredible. A problem that once seemed impossible can be solved simply by adding together infinitely many tiny pieces. But now comes the most important question of all. Why does any of this matter? After all, most of us aren't trying to calculate the area beneath random curves every day. So why is integration considered one of the greatest inventions in human history? The answer is simple, because integration isn't really about finding areas. It's about measuring accumulation. Imagine you're driving a car. Your speed isn't constant. Sometimes you're moving at 30 kilometers per hour. A few minutes later, you're traveling at 60. Then traffic slows you down to 20. If your speed changes every moment, how can you know the total distance you've traveled? You can't just multiply one speed by time, because your speed was never constant. Instead, imagine breaking your journey into thousands of tiny moments. During each tiny moment, your speed barely changes. You calculate the tiny distance traveled in that instant. Then you add all those tiny distances together. That's integration. Now imagine rainfall. A weather station reports how much rain falls every second. How do meteorologists determine the total rainfall during an entire storm? They add every tiny amount of rain that fell over time. That's integration. Think about a river. The water flowing past one point is constantly changing. Sometimes the current is stronger. Sometimes it's weaker. To calculate the total amount of water flowing through the river, Engineers add countless tiny amounts together. Once again, that's integration. Doctors use integration to understand how medication spreads through the body. Physicists use it to describe the motion of planets. Engineers use it to design bridges, airplanes, and satellites. Economists use it to estimate growth over time. Computer graphics use it to create realistic lighting and shadows in movies and video games. Even artificial intelligence relies on mathematical ideas built on calculus to improve data and improve prediction. Without integration, many of the technologies we rely on every day simply wouldn't exist. And that's what makes this idea so extraordinary. It began as a simple question. How do we find the area beneath the curve? But that single question unlocked an entirely new way of understanding the world. Because life itself is full of things that accumulate. Distance accumulates from speed. Water accumulates from rainfall. Energy accumulates from power. Knowledge accumulates from learning. Small actions accumulate into great achievements. And perhaps that's the most beautiful lesson integration teaches us. Great things aren't created all at once. They're built from countless tiny pieces. One step, one idea, one improvement at a time. Just like those tiny rectangles beneath the curve. Alone, each rectangle seems almost meaningless. Put together, they reveal something complete, something exact, something beautiful. The next time you see the symbol, integral, don't think of it as a distant number. Think of it as a reminder. A reminder that even the most complex problems can become simple when we break them into smaller pieces. And maybe that's true not only in mathematics, but in life as well. Thank you for joining me on this journey. I hope you'll never look at integration the same way again. If this video helped you understand the beauty behind calculus, please support the channel by liking this video, sharing it with someone who's learning mathematics, and subscribing to MathnexusbyNaustenka. Here, we don't just memorize formulas, we discover the ideas that change the world. And before you leave, here's one final question to think about. If integration helps us build an area from tiny pieces, then how do we instantly find the slope of a curve at a single point? That mystery leads us to another incredible idea, derivatives. We'll uncover that story in the next video. Until then, keep asking questions, keep exploring, and remember, mathematics isn't just a collection of formulas. It's the language that reveals the hidden patterns of our universe. This is MathnexusbyNaustenka. See you in the next one.